Uh, the present topic is Fermi level and Fermi energy, and before that we have studied about the uh, electronic properties of the solids. In this particular topic we will make our idea more clear about the Fermi level and Fermi energy. But before that, because this is a series of lecture, what we did in earlier two parts of the video lecture, the first one basically was focused on the properties of the metals and about the concept of free electron gas. In the second video lecture, basically the restrictions of the quantum mechanics is applied on the electron gas, and we use the approach of particle in a box on that, and from then we find the eigenvalues and eigenfunction for the free electrons. So this was the concept, and now in this third part of this video lecture I have to discuss about the Fermi level. So as one knows that electrons are fermions which obey the Pauli exclusion principle. So at absolute zero temperature, all the energy levels below a certain level will be filled with electrons, and the levels above this will be empty. So in this statement, what is the important point? That is the absolute temperature, and temperature is basically 0 Kelvin. So at this particular 0 temperature, the energy levels below a certain level will be filled completely, and above that level will be empty. So this is the boundary, and this energy level basically divide the two states. One, those are completely filled, and others are empty, completely empty. This level is basically assigned with the name of Fermi level, and the corresponding energy of this level is known as Fermi energy, that is basically symbolized by EF. So this is the first point, and the importance of Fermi energy level. So we are just discussing about the free electron gas, where we have considered that these electrons are free to move here and there, and there is no potential inside the metal. Outside or at the boundary, electron or these free electron basically feel the higher potential, and because of that they cannot leave the surface. These were the two restrictions on the concept on these electrons. These were the boundary conditions, right? So in metals, electrons have not uniform velocity. This is the first point, because in the metals all these electrons don't have same momentum, and because of that the velocity will be different. So no, ideally not uniform velocity, that is represented by the length of the vector in this particular figure. So large length of the vector represent the high momentum, and small length is the small momentum. So velocity of these electrons vary from lowest to the maximum value. A definite range of momentum in metal, and that range basically is decided by the Fermi level. So consider, if I hope this point is clear after this particular discussion, that electrons don't have uniform velocity. It basically varies from 0 to Vf, and Vf is the velocity in the Fermi energy level. So in earlier slide I have discussed about the Fermi energy level, that this is the extreme energy level which basically decide that all these energy states are filled by the electrons at absolute zero temperature. So in that particular situation this is true. So electrons will have a range of the energy up to the Vf, and obviously that will be energy. If we are talking about the energy, that will vary from 0 to Ef, and similarly for the momentum. So now consider n free electrons are in a box at absolute temperature. In ground state, these electrons may occupy different energy states, which can be so in momentum space, that is known as k space. The one can understand the idea of momentum space or k space similar to the coordinate space, as you see in xyz any event. So in the coordinate space of xyz, you define an event in terms of x, y and z. Similarly here, for these free electrons, we have considered the momentum space, that is basically depends on the momentum of different electrons which have different energy. So overall we have considered capital N number of free electrons. Electrons energy state in a metal can be determined by assuming a sphere of radius kf in momentum space, or you can say that is a k space, right? Because we know that k varies from 0 to the maximum value, and that is kf. So here this is the sphere of radius kf. This is kf. It varies from 0 to the maximum value is kf, and along the x-axis this is kx component, you can say, along the y direction, along the z direction. So these are three different axes, and the designed by the kx, ky and kz. So now we have considered here a momentum space. In that momentum space we are considering a sphere of radius kf, and the energy of the electron is defined by the formula E is equal to p square upon 2m, where p is defined in terms of k, that is h cross k. P is equal to h cross k. So this energy of the particle is equal to h cross square k square upon 2m. Maximum energy of the electron in k space is determined from the Fermi energy concept, right? So the electrons which are on the surface of kf, the energy of all those electrons will be ef, right? All these basically electrons which lie at this particular energy level, that is defined by the ef, will have the same energy. So ef is equal to h cross square kf square upon 2m, where m is the mass of the electron and h is the Planck constant, where h cross is equal to h upon 2 pi. Now we are using the uncertainty principle here, that is del x and del p is equal to h, where del x represent the uncertainty into the position when we try to measure the momentum of the particle, and delta p is the uncertainty at that time when we try to locate the particle exactly, right? So the product of these two uncertainty is equal to the Planck constant, and this is first law of the uncertainty principle defined by the Heisenberg and known as Heisenberg uncertainty principle. So when we use this uncertainty principle for this particular situation, where we have considered the length of the crystal is L, so delta x will be L, and delta p we know that that will be h cross k. So this is h cross k, H cross is equal to H upon 2 pi, and this is delta K. Right, so if I put the values of delta X and delta P from here, so this delta X is L, and this delta P is equal to H cross K, and H cross is equal to H upon 2 pi, and that is further delta K, and this is equal to H. So L into H upon 2 pi into delta K is equal to H. From here you can say that H cancel out, and as a result you have only this result delta K. So change into the delta K is equal to 2 pi by L, where L is the length of the material, that metal basically which we have considered, where we have bound those electrons. So in momentum space, K along any axis change in 2 pi by L, right? So as you know, earlier we have considered this is along Kx, here along this direction we have considered Ky, and this Kz. So this delta K basically represent the interval basically here, that is equal to 2 pi by L. So each segment along the x-axis, along the y-axis, that is equal to 2 pi by L, right? So this interval is of 2 pi by L. So here delta K is equal to 2 pi by L is defined by this way. That K2 minus K1 is equal to 2 pi by L. K2 minus K1 indicate to the delta K, and similarly K3 minus K2 successive interval is equal to 2 pi by L along the x-axis, along the y-axis, and along the z-axis. So K1 is equal to 2 pi by L, K2 is equal to 4 pi by L, K3 is equal to 6 pi by L, it means, right? So we have an idea about the variation of K, that is uniform along the x direction, y direction, and z direction. So delta K is equal to 2 pi by L. Now in momentum space, this 2 pi by L is the length along Kx, Ky, and Kz direction, right? So this is a sphere in momentum space, where Kf is the radius, right? So if there are basically defined these distances 2 pi by L along the x-axis, and similarly here 2 pi by L, and along the z-axis, that is 2 pi by L. So if I join all these basically points, so it indicate to the plane, one along the xy, and second is this yz, and the third one is along the this plane K, X, and Z. So when I join all these three faces, so it is equivalent to a cubic cell. So now you can further see that the volume of one cell in K space is 2 pi by L cube, where 2 pi by L is a one side. So here by using that idea, what we are just trying to do, we are just trying to find out the volume of a cell, right? And that cell represent to the energy state in which electrons basically are occupied. And now the next point, first what we did, we just try to find out the volume of one cell in K space, and that is 2 pi by L cube. And next we just try to find out the volume of the sphere in k space that is of radius kf. So the volume of this sphere will be equal to 4 pi by 3 pi kf cube. So I have to find out that how many cells can uh, mm, exist into this sphere. So for that, what I have to do, I have to just divide the total volume of the sphere by the one cell. So by this way I can find out the number of energy cell or energy state. So this is the way to find the energy states. So volume of a sphere divided by volume of a cell. Now the total number of energy states will be equal to 4 pi by 3 pi kf cube upon 2 pi l cube. So according to the Pauli exclusion principle, further, no more than 2 electrons can exist in one energy state. Right? So all the 4 quantum numbers could not be same for 2 electrons. So n is the principal quantum number first, L is second, Ml and Ms. These are 4 quantum numbers. So if 3 quantum numbers are same for the 2 electrons, the fourth one is spin quantum number will be different. And so here we did not consider that concept. So now we are introducing this concept that these are the total number of energy states, and in each state one electron basically can exist. So according to the Pauli exclusion principle, by using this concept we are multiplying it by 2. So one can find out the total number of the electrons in those particular energy states. One with spin up, that is ms plus 1 by 2, and second is ms minus 1 by 2. So nf is equal to 2 multiplied by this factor, right? And now this is, after simplification, n is equal to v upon 3 pi square into kf cube, where v is equal to L cube, where v is the volume that is defined by the L cube. So we have considered here it. So kf cube is equal to, if we have to find out the value of kf, then we have to simplify it again. So kf is equal to 3n pi square upon v and 1 by 3 of it. So here we have find out the total number of electrons that is represented by capital N in terms of v and kf, and here kf again in terms of n and v. So one can say that kf depends only on the ratio of number of electrons and the volume of the cell. So that is number of electrons per unit volume. So kf does not depends on the mass of the electron. Kf is the momentum at the Fermi energy level, and it does not depends on the mass of the electron. It is independent from the mass of the particle. So these were two mathematical result. One is for the n and second is for the kf. Now we know the Fermi energy, that is defined by h cross square upon 2m into kf square. So if I have to find out EF, then I can put the value of kf here. But before that, if suppose I have to find out the velocity of the particle, these free electrons, then I have to use this formula of EF is equal to 1 by 2 mvf square, where Vf is the velocity of electron at Fermi level. So now comparing these two parts of energy, 1 by 2 mvf square is equal to h cross square kf square upon 2m. So by comparing these two results, by putting the value of kf in this equation from here, so one can find out the velocity at the Fermi level of electrons, that is h cross upon m into 3n pi square upon v raised power 1 by 3. So by this way one can find out the energy, momentum, velocity of the particle. So these result basically are summarized here. So how one can find out the total number of the electrons or number of the states, because this n came from the density of the states. Here n is the result of 2 multiplied by the density of states, right? And kf is equal to 3n pi square upon v raised power 1 by 3, that is independent from the mass. And again velocity in terms of h, m, n and v. So all these characteristics of the particle, of a free particle, one can explain from here, or one can determine all these things basically for a free electron. So now in the next part of the lecture, the fourth part of the video lecture, we will discuss about that. Now we have the idea of the electrons, that these number of the electrons, this is the energy, this is the velocity, this is the momentum, everything we have about the free electrons, right? So by using these characteristics of the electron, one can define the properties of the metal, right? So now in the next part of this fourth part of this series of lecture, we will try to find out the distribution of the electrons in different energy states which